I'm beginning a new series on how not to teach AP pre-calculus. This is coming up because I'm tutoring some AP pre-calculus students and I'm appalled by how the teachers are teaching this course. It's typical algebra and pre-calculus topics, but for some reason in this AP pre-calculus class, they're teaching it so badly and incorrectly, per se. We'll get to that in part two. I already have that planned. Actually, part one is this example I'm giving is totally incorrect as well. So if you're a teacher and you're watching this, maybe this can help you understand what students are confused about, at least the ones that I encounter, and what to avoid and to be careful about. If you're a student, hopefully this helps clarify things. Okay, so this is what motivated part one. So I saw this in my students' notes. So the teacher posted her completed notes. You would expect that they're, for the most part, accurate, but there was a big mistake, especially for this new concept that they're teaching, new topic that they're teaching about adding rational expressions. So here's the example where it all went wrong. Okay, so we want to add these two rational expressions. What is a rational expression, by the way? It's like some polynomial divided by another polynomial. Okay, so this is a polynomial. If you expand this bottom out, it's also a polynomial as well. Okay, so when we want to simplify and combine these two, it's like a fraction. We want a fraction with numbers. We want a common denominator. In this case, they are, so we can just directly add the numerators and then just keep the denominator as is. Okay, so that's what happened over here. And I'll give the teacher credit. Her work was actually really neat and well written like this over here, step by step. Nice equal signs to show equality. Okay, so from here, we can simplify, combine like terms, minus 8x plus 3x, that's negative 5x here, negative 5 and a negative 1, that makes a negative 6, okay? And can we simplify further? This is one of the ideas. Well, for simplifying rational expressions, well, we can factor the numerator as x plus 1, x minus 6. And then notice that these x minus 6's, they're same thing divided by each other, so it divides out to a 1, yeah, so they cancel. You can draw those cross out lines if you want, and that simplifies to x plus 1 over x plus 4, okay? And then notice here, we can't divide by 0, right? So we have a restriction that x cannot equal to negative 4, because when x is negative 4, we'll be dividing by 0, okay? However, grave error happened here. This is actually what a lot of students do wrong, and yet the teacher does it wrong. This is a critical concept in this section. And yet the teacher did it wrong and posted it for her students to reference. I totally don't understand. Okay, I understand that sometimes mistakes happen, but this is a critical concept. Okay, so what's the missing concept? Okay, so I'll go over it if you totally missed it. Okay, the concept of equality needs to be emphasized here. Okay, so I'm going to motivate by this example over here, or two examples, and then I'll go up to build up to rational expressions. Okay, so here's the example with just numbers. Okay, 1 plus 2 plus 3. We can simplify it by first adding the first two terms, order of operations. They're all adding, so we go left to right. 1 plus 2 is 3. Okay, and we can do 3 plus 3 equals 6. Okay, so when we write it like this, we're communicating that 1 plus 2 plus 3 equals 6, or it's the same as 6. One version, the 6, is just the simplified version of 1 plus 2 plus 3. That's why we say simplifying. It's just less terms and neater. Okay? That's example 1. Here's an example with the variables now. Okay? Let me get rid of on both sides. Okay? So if we have 3x plus 4 minus 2x minus 2, well, we can group the like terms together first. So equals 3x minus 2x plus 4 minus 2, okay? And then we can simplify. 3x minus 2x, that is just 1x, so x. And then plus 4 minus 2, that is a plus 2. So we're communicating that 3x plus 4 minus 2x minus 2 is the same as x plus 2, okay? This x plus 2 is just the simplified version of this guy over here. Okay, and in this case, let's notice that x can be anything and the equality is still true. no matter what value of x we plug into 3x plus 4 minus 2x minus 2, we'll always get the same value out when we plug in the same value of x as x into x plus 2. Like, for example, x equals 0. You get 0 plus 4 minus 0 minus 2, which is 4 minus 2, which is 2. Yeah? And then here, 0 plus 2 equals 2. Okay? So x can be anything. Equality is still true. Okay? Now let's move on to the rational expressions. Okay? Rational functions. Let me change it to expression. We're not really dealing with functions here yet. Okay. Maybe I should check my work. Okay. But anyway, so let's revisit the same example. Okay. If we start with this guy over here, x plus 1, x minus 6 divided by x plus 4, x minus 6, notice that x cannot be negative 4 and x cannot be 6. We have these two restrictions. We'll be divided by 0, which cannot happen. Okay. Now, if we simplify this expression up here, so the x minus 6 is canceled, like I was saying earlier. So we're left with x plus 1 over x plus 4. When we just focus on this, without knowing any of this beforehand, if we just focus on this, it looks like our only restriction is x cannot equal to negative 4. Okay, now let's tie in the concept of equality here now. If we're trying to say that x plus 1, x minus 6 over x plus 4, x minus 6 is equal to x plus 1, x plus 4, okay, we actually need to keep both restrictions from the left-hand side. Why is that the case? So here's the concept of equality. On the right-hand side, this side over here, the simplified version, we can totally plug in x equals 6. It's not an issue. We would actually get a value of 7 over 10, okay? Now, we try to plug in the same value of x, so x equals 6, into the left-hand side. We run into an issue because we're dividing by 0. So let's think about it. How can we, when something's divided by 0 is undefined, right? So how can something undefined equal 7/10? That's not logical, right? Therefore, to keep the equality possible, that's why I'm emphasizing this concept of equality. To keep the equality, we have to keep the strictest restrictions. So we have to also say that x cannot equal to 6. It's fine to plug it in onto the right-hand side, but we have an issue on the left-hand side. So we also say that x cannot equal to 6. If we state that restriction along with x cannot equal to negative 4, then it's fine. If we state those two, all other values of x are fine. The equality will be true. Okay, that's the missing concept that I hope the teacher emphasized, and maybe she just totally forgot to write it. Okay. All right, so here is doing the example corrected, actually. This is probably a little overkill, to be honest, but this will emphasize the concept, hopefully. When we start from the beginning here, we have the original restriction, x equals negative, cannot equal to negative 4, and it cannot equal to 6 as well. This notation should be fine. Negative 4 comma 6, okay? We bring this down all the way to the end. That's the correct way. Because when we say equality equals, this restriction has to still be there in order for it to be equal. So even though we simplify down here by canceling the x minus 6's, the restriction still has to be there for the equality to be true. Hopefully this concept makes sense, and now you understand why we have to keep both restrictions in this particular example. Don't make the mistake that the teacher did, please.